All right. Now we're going to write a Taylor and Maclaurin series. So what this is we can take a function like this super fun function, e to the x, and we can represent it, well, we can approximate it using a polynomial. Oh my gosh, that's amazing. So the polynomial itself is not the same value of the function, but it can be really, really, really close. Okay. The more terms you get in your series, then the closer we get to the actual value of the series. Okay. So let me show you what I'm talking about. What we're going to do is evaluate f of x is equal to e to the x. Okay, so this is my series. This is my function, and I'm going to write the function as a polynomial. So the polynomial for this function would be 1 plus x. That's a two-term polynomial. Then we can represent it with more terms. So 1 plus x squared over 2 factorial plus 3 squared over 3 factorial. Or we can write it with more terms, 5 terms, 6 terms, 7 terms, 8 terms. And the more number of terms we get, that sounded weird, the closer we are to actually approximating the actual value of the function. So let's take a look at our actual function here. Actual function. So if I plug in e to the 0, I get 1. E to the 1 is about equal to 2.7183. E to the 2 is about equal to 7.3891. Okay, so those are the actual values. Now let's see what happens when we plug in 0 into the polynomial for each one of these polynomials that's supposed to approximate the value of e to the x. Okay, so this is a two-term polynomial, so it's not going to be the best approximation, but basically I'm going to plug in 0 for x, so I get 1 plus 0 is 1. Huh, matchy matchy. Okay, so then I get, if I want to approximate e to the x at x equals 1, I plug in 1 for x. So I get 1 plus 1 is 2. Okay, 1 plus 2 is 3. Okay, this is not, you can see this is not the best approximation. But let's go for more terms. So when I substitute 0 in for x, I get 1 plus 0 squared over 2 factorial plus 0 cubed over 3 factorial. And I did that in my, it's 0. It's 1. Okay, again, very close. That's our starting point, basically. So let's go ahead and evaluate when x is equal to 1. This is going to give me an approximation of e to the 1. So I'm going to do 1 plus 1 plus 1 squared over 2 factorial plus 1 cubed over 3 factorial. And this is about equal to 2.66. Ooh, we're getting pretty close. Okay, I'm going to do the same thing, but evaluate it at x equals 2. So 1 plus 2 squared over 2 factorial plus 2 cubed over 3 factorial is equal to 6.33. Again, we're a little off from e squared, but we're getting better. Okay, so now with polynomial with 5 terms, when I substitute in the values, I'm not going to plug them in this time. I get 1, 2.7167, and then 7.2667. Look how close we are to our actual value. Wow. Wow. Okay, anyway, so long story short, we can use a polynomial to estimate the values of, or approximate the values of, our actual function. So we're basically writing these polynomials based off of the rate of change. So the first derivative plus the second derivative plus the third derivative, so on and so forth. It's really cool. All right, so to write a power series, we define the degree of the power series as the highest degree that you see. So for this one here, the degree would be 3 because the highest degree is x cubed. Okay, the one below, the highest degree is to the x to the 1, so the degree would be 1. The one below, the highest degree is n, so the degree of the polynomial would be n, okay? 1 minus x to the 5th over 2, the degree is 5, because the highest degree is 5. P of x is equal to 5, the degree is 0, so I'm just going to write 0. So the degree is 0, okay? All right, so the definition of a power series is if x is a variable, then the infinite series of the form the sum from n equals 0 to infinity of a sub n times x to the n is equal to a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x cubed plus blah, 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 blah. This goes on forever, okay? So we call this a power series, or more generally, an infinite series in the form of, okay, of the sum from n equals 0 to infinity of a sub n times x minus c to the n. So this is if we're not centered around 0, we're centered around some shift, okay? So basically the same thing, we just expand it. We call this a power series centered at c. So instead of being centered at 0, you're centered at c, which c is just some value. So looking at these next series, I want you to tell me where the series is centered around. In other words, where are we starting from? Okay. So looking at the structure, I see that what I'm multiplying is x minus 0. So the center is at c is equal to 0. Okay. This one, I can look at my rule, x plus 1 to the n, and then every term has that x plus 1. We are centered around c is equal to, because it's horizontal, you're going to shift to -1. Okay. We're centered around -1. The last one, we can see in our rule that we have x minus 1, x minus 1, x minus 1, x minus 1. So we are centered around c is equal to +1 because it is opposite, the opposite sign. Okay. All right. So any convergent power series for a function can be written from the basically the same. Okay. That form is called a Taylor series, named after Brooke Taylor. All right. So a Taylor series is a function that has derivatives of all orders at x equals c. Then the series is, so if it has derivatives, then the series is the sum from n equals 0 to infinity of the derivative of c, so the derivative at c, over n factorial times the factor that you're centered around, so x minus c to the n power. And then we expand that to be f of c plus f prime of c. So first derivative of f centered at c, yeah, times x minus c. The second derivative of f at c, times x minus c squared over 2 factorial. Basically, this first term is over 1 factorial, but since it's 1, you just don't have to put that factorial. And then the first term is over 0 factorial, which is also 1, so we just don't put that. Okay. All right, so this is how this works. If you have a Taylor series, so a series written in the form with all these derivatives, then if the series is centered around C, then it's a special kind of series, and we call it a Maclaurin series. Okay, Maclaurin series is just it's just a special Taylor series that's centered around 0. Okay. Taylor and Maclaurin series that have an infinite number of terms is called a series, okay? A Taylor or Maclaurin polynomial will have a finite amount of terms, so it'll be written more like our polynomials from above, okay? Those are polynomials, not series. Infinite is series, polynomials is finite. Okay, so this sounds really bad, but it's not that bad. Okay, so first we're going to form the first, second, and third degree Maclaurin polynomial, as well as the general, then we're going to figure out the general term for f of x equals e to the x. So the general term means like the sum, we're going to figure out the rule to write it as the sum of a sub n, okay? So what am I adding up in my series, okay? So the first, second, and third degree polynomial means that we are using a polynomial with x to the first power, a polynomial with x to the second power, and a polynomial with x to the third power. So really that means 2 terms, 3 terms, 4 terms, okay, because we're starting with n is equal to 0. Okay, so the way we do this is we set up on the side, we say f of x, we're estimating f of x is equal to e to the x, and then what we have to do is to expand our polynomial, we have to evaluate f of c. We are a Maclaurin series, so we're centered around 0, okay? So I'm going to evaluate f of 0 is equal to e to the 0, which is 1, okay? Then in the next term, I need to multiply the first derivative at c times x minus c. So I need to find f prime of 0. So we take the first derivative. Okay, and the nice thing about e to the x is that the derivative is always e to the x, so f prime of 0 is also equal to 1. Okay, we're going to do this a bunch of times because I need to find the first, second, and third degree polynomial. So I need like 2, 3, and 4 terms. So I need, that would be, those 2 terms would be the first degree. Add that term for a second degree, and add this term for a third degree. So I need to take the third derivative here, okay? So f prime of x, f double prime of x is equal to e to the x, and f triple prime of x is equal to e to the x. F double prime of 0 is equal to 1, and f triple prime of 0 is equal to 1. Okay, we're going to set this up. Now we have the polynomial P1 of x, means the first degree polynomial, okay, is equal to, we're going to use our rule from above, f of c plus f prime of c times x minus c. Okay, we know that our c is equal to 0, so what we are evaluating is f of 0 plus f prime of 0 times x minus 0, which would be f of 0 is 1 plus f prime of 0 is 1 times x. So the approximation, a 2-term polynomial that approximates e to the x would be, x plus 1, or 1 plus x. All right, so we're going to do our second degree polynomial, which will so this is a 3-term polynomial that is used to approximate e to the x. We kind of already saw this before. So it's P2 of x, means the second degree, is equal to, we use our rule from above to expand out any power series. We do f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared, there's our second degree, over 2 factorial. Okay, so we're going to evaluate. We get P2 of x is f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 times x minus 0 squared over 2 factorial. So that simplifies. We know f of 0 is equal to 1 plus f prime of 0 is also equal to 1 times x plus f double prime of 0 is equal to 1. It's so nice. Times x squared over 2 factorial. This would be the second degree polynomial that estimates or approximates e to the x. Okay, so for the third one, we're going to do the same thing. F of c plus f prime of c times x minus c plus f double prime of c times x minus c squared over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial. We're going to add that fourth term. So we're going to go ahead and expand that. So p sub 3 of x is f of 0 because we're evaluating at c, or we're centered around c is equal to 0, okay, plus f prime of 0 times x minus 0 plus f double prime of 0 times x minus 0, I'm not going to put that, squared, over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial, okay, so p sub 3 of x is 1. Remember, we get those from our table that we built earlier, plus 1 times x plus 1 times x squared over 2 factorial. So it's the same as our second degree polynomial. Now we're just going to add one more term, which is f triple prime of 0 is 1. And then we multiply that by x cubed over 3 factorial. So when we evaluated earlier in our table, what we were looking at were the power series or the Taylor series that help us to evaluate or approximate e to the x. So this is the rule to expand e to the x into a polynomial. Okay. All right, so we're going to do another one. We're going to do the fourth degree polynomial, which means fourth degree means 5 terms, because the first term uses the actual value of the function, not the derivative. So we're going to end up with 5 terms. We're approximating e to the x centered around x equals 1. So that means that this is c is equal to 1. Oh, we didn't do the general term. So the general term would be the sum from n is equal to 0 to infinity of, I can see the 1 stays the same, okay? So there's always a 1. The signs are always positive, and I get x to the, when n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, I get x to the n power, and that matches here, x to the n power over n factorial. So this is the general term. This is the sum of our polynomial, the general term of our polynomial. All right, so we're going to do number 4, our 5 terms centered at c. So I need to start with f of x is equal to e to the x, and then I need to take the derivative up to the 4th derivative. So f prime of x is e to the x, f prime of x, double prime of x is e to the x, f triple prime of x is e to the x, and f to the 4th derivative of x is equal to e to the x. Okay, we are centered at 1, so we're going to evaluate each one of these functions at x is equal to 1. So f of 1 is e, f prime of 1 is e, f prime double prime of 1 is e, f triple prime of 1 is E. F, the fourth derivative of f, evaluated at 1, is also E. Okay, so we're going to set this up. We get the polynomial of 4, the fourth degree polynomial of x is equal to, and we have to use our rule from above. So we get f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared. The degree and the primes and the derivatives always match, over 2 factorial plus f triple prime of c times x minus c cubed over 3 factorial. And then we have one more term, which is f, the fourth derivative of f times x minus c to the fourth over 4 factorial. So I can write, we're centered around c, so this is going to be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared over 2 factorial plus x triple prime of 1 times x minus 1 cubed over 3 factorial plus f, the fourth derivative of f times x minus 1 to the fourth over 4 factorial. Okay, now we're going to evaluate. So f of 1 is equal to e, because we did all the work on the side over here. Okay, so f of 1 is e plus f prime of 1 is e times x minus 1 plus e times x minus 1 squared over 2 factorial plus e times x minus 1 cubed over 3 factorial plus e times x minus 1 to the fourth over 4 factorial. So this is my fourth degree polynomial. And now we're going to write the general term. Okay, so the general term is the sum from, and you kind of get to choose where you want to start your n equals 0 or n equals 1. But I noticed that if I start at n equals 0, then, oops, that should be a, that the term number matches the factorial and it also matches the degree. So it seems like it'd be easy for me to start with n equals 0 in this case. Okay, so I'm going to go to n equals 0 to infinity times e is constant, so I'm just going to go ahead and write e. It never changes. The x minus 1 never changes in each one of the terms, but the degree does. So the degree of the first term, n equals 0 term, would be 0. The degree of the second is 1. The degree of the third is 2. So that matches with the value of n. And then I'm dividing by n factorial. So that is my general term. Okay, we got a couple more. Two more, so a couple more special series here. We're going to form the Maclaurin series for f of x is equal to the sine of x. So basically what we're going to do is we're going to write our power series. So write it as an infinite polynomial, a polynomial with infinite terms, and then we're going to find the general term. Okay, so I am going to, a Maclaurin series centers around 0. So I'm going to start with f of x is equal to the sine of x. And then I'm going to take the derivative, which is cosine x. I'm going to take the derivative of that, which is negative sine x. I'm going to take the derivative of that, which is negative cosine x. And then I remember that they repeat. Okay? So I now need to evaluate f of 0, which is sine 0, which is equal to 0. And f prime of 0 is cosine 0, which is equal to 1. F double prime of 0 is negative sine 0, which is 0. And f triple prime of 0 is negative cosine 0, which is negative 1. So the fourth derivative of f at 0 is equal to sine 0, which is 0. So these are all going to repeat. The fifth derivative at 0 is 1. The sixth derivative at 0 is 0. The seventh derivative at 0 is negative 1. Okay, that should be enough. Okay, so I have the polynomial. We're not going to put a subscript because we're just going to write a series. So it goes on forever. The p of x is equal to f of 0, okay, plus f prime of 0, remember that's my c value, times x minus 0, which is just x, plus f double prime of 0 times x minus 0 squared over 2 factorial, plus f triple prime of 0 times x cubed over 3 factorial. Okay, so that's the pattern. Now let's plug in the numbers. So we get f of 0 is 0 plus 1 from f prime of 0 times x plus f double prime of 0 is 0 times x squared over 2 factorial plus the third derivative would be at 0 is negative 1 x cubed over 3 factorial. The next term is made up of the fourth derivative at 0, which is 0 times x to the fourth over 4 factorial plus the fifth derivative at 0, which is 1 times x to the fifth over 5 factorial plus 0 times x to the sixth over 6 factorial plus the seventh derivative at 0 would be negative 1 times x to the seventh over 7 factorial. And I'm like, whoa, that's a lot of zeros. So I'm going to cross them out, cross out all my zeros, and rewrite this. Okay, and then I put plus dot 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 because this is going on for infinity. So the polynomial is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. Plus, that's how it happened. It goes on forever. Okay, so what is the general rule? The general term would be, and I have to decide, do I want to start with n is equal to 0, 1, whatever, okay? I'm going to start with n is equal to 0 and try to make a rule. This is my second term, this is my n equals 0 term, my n equals 1 term, my n equals 2 term, and my n is equal to 3 term, okay? So let's see, x's all stay, and the degree of the x looks like it is n times 2 plus 1. So if I double the n value and then add 1, I get 5. If I double 3 and add 1, I get 7. Okay, so this is 2n plus 1 is the degree. Over the factorial is that same rule, 2n plus 1 factorial. But I also noticed that the signs change, okay? So I know that it's alternating, so I'm going to have to multiply by negative 1 to the n maybe. So if I look at n is equal to 0, if I plug in 0, I'm going to get a negative number, okay? Sorry, n to the 0 is positive 1, so that's going to be positive. N to the 1, negative 1 to the 1 is negative 1. Negative 1 to the 2 is positive 2. So it looks like just to the n power will give me a degree that makes my signs alternated in the correct pattern, okay? So the general term is this. Oh, and I forgot the infinity. From n equals 0 to infinity, and this is my general term. Okay, last one. So the Maclaurin series, so that means that we are centered at 0 for cosine of x. All right, we've done a lot of this work. So f of x is equal to cosine x, f prime of x is equal to negative sine x, f double prime of x is equal to negative cosine x, and f triple prime of x is equal to sine x. Okay, we're centered at c, so we're going to do f of 0 is equal to 1, f prime of 0 is equal to 0, f double prime of 0 is equal to negative 1. We are not surprised that every other term is going to cancel out. The fourth derivative at 0 is 1. The fifth derivative at 0 is 0. The sixth derivative at 0 is negative 1 because all these values are repeating every 4 derivatives. Okay, so I have the polynomial of x, p of x is equal to f of 0 is 1 plus f prime of 0 is 0 times x plus negative second derivative, so negative 1 times x squared over 2 factorial, plus third derivative of f triple prime of 0 is 0 times x to the third over 3 factorial, plus fourth derivative at 0 is 1 times x to the fourth over 4 factorial, plus 0 times x to the fifth over 5 factorial, plus negative 1 x to the sixth over 6 factorial, plus another 0 term. Why not? Okay, we cross off the ones that cancel. So p of x would equal 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus some infinite number of terms, and that is equal to the sum of, let's try n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. Ooh, that's nice because it looks like if I just double each one of these n values, I get the value of the factorial and the value of the degree. So I get 2n on the bottom, factorial, 2n factorial. And then on the top, I get x to the 2n. And the signs alternate again. So negative 1. And then it looks like all of my odd degrees, I want a negative. So I can just use a regular to the n. So that would be my general term. So this is the polynomial that basically gives me the value of cosine of x. That's so cool. And this is the polynomial that basically gives me the value of sine of x. This is the polynomial that's going to give me the value of e to the x. And that is us using a power series to write these functions as a polynomial. Whoa. Okay, more tomorrow. Bye.